Yeah, okay. My name is Subashree Venkatasubramanian. I'm a rising sophomore at Columbia studying computer science and operations research. And my project is focused on capturing heavy-tail behavior in the ClimSim dataset. So first, for some background, Mark did a great job at explaining how in the precipitation variable, we see a lot of extreme values. And that's kind of similar, well, that is what a heavy-tail behavior, a heavy-tail variable is, because we see, especially like around like the edges of the distribution, compared to a normal distribution, there's a higher concentration of extreme values. And specifically with precipitation or climate variables, this is really important to predict because we want to be more aware of extreme phenomenon. And also it's really important in the scope of machine learning because a lot of machine learning techniques nowadays use a loss function called mean squared error, and MSC loss doesn't assume a heavy-tail distribution, it assumes a normal distribution. So that heavy-tail behavior might not be fully captured by using an MSE loss or a normal distribution prior trained machine learning or neural network. So that's kind of the background as to why I decided to focus on this. And for my methodology, the first step was to pre-process the data. So I focused on the precipitation variable in the ClimSim dataset because just universally precipitation data does have, it does show pretty strong heavy-tail behavior. And so there's a lot of pre-processing and log normal transformations to do, taking the raw data, which is like shaped in this like gamma distribution, and then filtering out the values which are very, very close to zero. The scale is about 10 to the negative 8, 10 to the negative 9. And at that point, the data can kind of conflict with the transformations later on. So yeah, filtering out those really low values by experimenting with different thresholds and finding the one that's best capturing heavy-tail behavior while still filtering out unnecessary data. And then we apply like a log normal transformation to see a different shape of the data as well, which is going to play into the picture later on with the Bayesian neural network. And then we can also visualize the heavy-tailed behavior by using these QQ plots. So these are quantile plots, and they basically show us how these distributions are shaping according to a normal distribution. So from this slide, you can see on the right how a normal QQ plot is kind of straight, and a heavy-tailed QQ plot has this very interesting skew for both the left and the right sides of the distribution. In this case, it's because there's a lot of uniform values on the left side, that skew is more prominent on the right side. So you can see that in both of these, and you can also see how once we apply the log normal transformation, that skew is less evident, but it is certainly still there. And then this was a big part of the research, so understanding a Bayesian neural network architecture. I was really interested in using a Bayesian neural network, also called like a BNN, I'm creating that term, because Bayesian inference is taking into account prior information or prior like hypotheses, and then kind of using that to aid the training along the way. But in this case, we want to really be focusing on the shape of the distribution. So in a Bayesian neural network model, we can input weights into our neural network, but also look at specific prior and posterior distributions and see how those are changing along the layers, and really try to focus on getting our y, in this case, the precipitation variable, to follow that heavy-tail distribution at the end of our training. And the loss function that we're using for this is the NLL, our negative log likelihood loss. So if we think of it as like a maximum likelihood estimation problem, we want to maximize the likelihood by minimize the loss value. So this is just an example with a normal PDF, and that would be translated to a different NLL loss depending on what prior distribution we're setting. So yeah, and then looking into some possible Bayesian priors based on the shapes of our data. So we can see from this very interesting curve of our filtered precipitation data, it looks very similar to a gamma PDF. So I had this kind of like preconception going in, oh, maybe the gamma prior would be a good estimator for this data. And then we can also see once we apply the log normal transformation, it looks kind of similar to a Cauchy prior, that like heavy tail distribution, but also we can experiment with log normal or Gaussian priors just to see how different metrics are scoping in the Bayesian neural network setup. And then that's like my model setup with the layers, and then looking specifically at the distribution lambda for our output. Okay, and so this is a baseline. So the scaling is a bit off, so it looks really weird in the plot. But this is actually just really concentrated. So that's why it looks like a line, but it's actually a distribution, just very concentrated. And we can see from our loss, we do have a decent loss value, but a lot of the data just doesn't, like we can see that it just isn't correct. There is something very wrong with this. And I kind of hypothesize at this point, maybe it's because we're not taking into account the distribution as much as we should. But then when we look at, once we start using the Bayesian neural network model, the model prediction versus actual data kind of visualized as a histogram does look a lot more, it looks better. And so we can see the prediction versus actual here. And then we can also see in our loss values, the R-square values are negative, which is not a good sign. But I have a few hypotheses about why that is. I think it might be just because of the quantity of data. So while the distribution seems similar, it's not perfect. And anything that's outlying is going to be really, like the magnitude is really going to be increased because just the sheer number of data points, which might work against us in the R-square test. So yeah, I think for future research, definitely doing some more correlation-based tactics and kind of trying to do scatter plots and visualize the data that way might be helpful in improving this. And then this is with the Gaussian prior filtered on the log normal data with the NLL loss. We can see this is a step closer to what we want to get to, but there is definitely still something missing in terms of like capturing like the tail behavior for the predicted versus actual histogram. And then I also tried for our gamma prior approach. So the gamma prior can be applied both to the log normal data and to the regular filtered data, which is really, really interesting. And yeah, I saw that we can see from like the loss functions, it's training well, but also the prediction does seem to be much more accurate in both cases, which is really interesting as well. So yeah, I found like just through my initial testing, and I've only been working on this for a few weeks because I kind of switched from creating my own loss function, which was based on like quantile regression, to this problem just a couple of weeks ago after a really good suggestion from Professor Mant. So I do really appreciate that because I'm really happy with the work that I've done, and I hope to be able to continue and kind of work on this a bit more. But we can see that the best, in my opinion, the best predictor was the gamma prior, the Bayesian neural network scheme with the gamma prior distributions. Not only did it both work for the log normal and the filtered data, but the loss values and the Pearson correlation coefficient values are quite good as well. And the best correlation was, and that continued with all of the standard metrics, which is really interesting as well. Okay, and then some takeaways and future research opportunities with this. We can definitely see the benefits of using a BNN because in the histograms, we can see that the shape of the distribution is much more effectively conveyed after training with the BNN architecture. And we can also see that the most effective prior network, the most effective prior distribution is very dependent on the shape of the Y data. So this might not be generalizable to other shapes of distributions that might require other training with different prior distributions. But definitely for heavy tail distributions, and this can hopefully be generalized to other variables in the ClimSim dataset as well, maybe like the solar insolation flux, I believe, and the input and output for that. We can see maybe this can be generalized to those approaches as well. And for future research, actually with climate change, unfortunately, there is an increase in extreme behavior for a lot of climate variables, not just precipitation, but many other variables as well. So there is a growing importance in predicting heavy-tailed behavior. And there are like a lot of opportunities for taking this further by visualizing successful predictions with QQ plots and looking more into other accuracy metrics as well. So yeah, I think that was my presentation. So I'll take any questions. And I do also just want to say thank you so much to all of our mentors for all the help throughout this process. But I'll do Q&A first.
Hi, great presentation. I wanted to ask more about the setup. So what exactly is your input data? How many dimensions does it have? How many training samples do you have?
Yeah. So the input data in this case, so I just used for my X the specific humidity and the pressure, I believe, for the input data. And then the output is going to be the precipitation variable, which is, as Mark described, created by combining the rain rate and the snow rate. And then the dimensionality, it's quite large. They're about, I think, I'm trying to think of the exact number. It changes depending on the amount of filtering you do. So the threshold that you choose actually really impacts the shape of the data pre and post normalization. But I think I had somewhere in the hundreds of thousands of data samples. I want to say consistently above 200,000. So yeah, and I think definitely this result would also be dependent on the size of the data, because that is very important in the shape of the distribution as well. So yeah.
Yeah, I just have a comment for you and Sammy, actually, because you both had a negative R-square. It could indicate that your bias from the neural network is even larger than the variance of the neural network, of the predicted value of the target itself. So yeah, I think maybe you can try further tuning the parameters of the neural networks. I think you both used a relatively small neural network setup. Maybe later you can try some different tuning for the network. Yeah.
Yeah, I think that would be really interesting. And I have a feeling Sammy's going to say this, but we were actually thinking about like an ensemble approach too between like the variational autoencoders and kind of this concept, because those do assume like a normal distribution for the data. And it could be interesting to see how changing the shape of distribution would affect the accuracy of the predictions. So yeah.
So that's the stuff here right there. Could you go back to your results table? So when you're calculating like the regularized and non-regularized loss, those values are MSE, right?
So kind of. The reason why I had to do that, not only, well, first it was because once you applied the log, the scale of the data completely changes. So the whatever loss value you're getting could be similar, but it might not necessarily reflect the same thing when it's compared to the overall data. And then also the NLL loss and the mean squared error loss just between the baseline and then the training for the Bayesian neural networks is completely different in the sense that with NLL loss, you can actually have like pretty high like negative values. Like you can see in this plot, like we actually have like a loss of -16, which in any other setting would be like, what is going on? But with NLL, I think because it's e to the -16, that would be like the, in scale that becomes something around like 10, I would say like the scale of like 10 to the -9, I believe. And then when you look at it into perspective with the actual data values, you end up with the regularized loss function. So just so that it can be translatable between MSE and NLL, I had to kind of implement that.
Okay, but would that be a reason why the loss for like the sorry, can you go back? When it was like looks like a direct, like just a spike. Like, could that be why the spike has such a low loss? Because like the loss there is MSE, which isn't actually like a good metric.
This loss?
The one that's like a Gaussian prior, but it's just like a spike.
Wait, let me see.
Yeah, that one on the left.
Oh, this one?
Yeah, like is that why the loss might be so low? Because the loss metric being used is actually like not good.
Oh, you're saying like the mean squared error
Yeah.
loss is not applicable there?
Yeah.
I think that could be interesting looking into, and that's what I was doing actually before I kind of switched into the Bayesian framework, looking at how different loss functions are affecting the outputted data after training with the neural network. So yeah, I did find that there are a lot of other approaches, and I think quantile regression loss would probably be like a really good approach to take here, because we want to once again look more at the shape of distributions and try to like minimize the distance in the quantile plots. So yeah, that could be interesting. Thank you.
Yeah.